North Carolina, a raging inferno threatens citywide devastation.
The fire department started riding around saying, please get out of your homes.
Command to all units, we're going to evacuate the scene. Leave any equipment on the ground, just leave it.
Catastrophe slices the TransCanada highway in two.
Traffic was backing up for miles. Every good that is being transported across Canada is going across this bridge.
In New Zealand, an apartment building with a potentially dangerous weakness.
If the support fails, there's a risk of total collapse.
And on the Swiss-German border, a bridge build that was way off course.
Da hat man festgestellt, ups, hier stimmt was nicht. Ja, unglaublich.
With big builds, even the smallest fail can trigger a huge disaster. From miscalculations to misunderstandings, or just plain bad luck. These catastrophes are every engineer's worst nightmare. With big engineering, design and construction are just two parts of the equation. Sometimes problems arise in day-to-day operations. Like this disaster in North Carolina that struck fear into the heart of a community.
You couldn't see the sun. You couldn't see the sky.
Lives on the line as fire raged out of control.
There were people sleeping in their homes 750 feet away.
With an entire town facing total obliteration.
Every bit of ingredient for a massive explosive device was right here.
This could have been the biggest land-based explosion in the U.S. since nuclear testing in the 1950s.
Winston-Salem, North Carolina, got its unique name back in 1913, when two neighboring towns merged into one, bringing together both people and industry.
At the time, Winston-Salem was North Carolina's largest city and thrived thanks in part to an industry that's fallen out of favor in recent years: tobacco.
And there was one product that really kick-started things: chewing tobacco. Journalist Chad Nance explains.
They decided to start adding additives to the tobacco, and they found that people really liked the tobacco if it had sugar, honey, and some other additives in it. So therefore, their business took off.
Within decades, the tobacco industry was booming. Farmers needed to ensure they could keep up with the demand for raw ingredients, and fertilizer was key to making that happen. Much of it came from this plant, built in the 1930s.
It was about the tobacco industry. It serviced the tobacco farms in the surrounding counties of Stokes, Surrey, and Davison.
For the next 80 years, the plant produced and stored a key ingredient for healthy crop growth: ammonium nitrate. John Merle is an associate professor of chemistry.
So ammonium nitrate is a great nitrogen source. Probably the most important use is in fertilizing plants.
The problem is nitrogen is highly soluble, so it's easily washed out of the soil by winter rains. The easiest way to replace it is with fertilizer.
Although vital for healthy crops, fertilizer-grade ammonium nitrate has a risky characteristic, making proper storage an absolute necessity.
It should be stored on its own in a well-ventilated area. Issues arise when temperature and pressure builds up, and this allows reactions to take place and allow it to explode.
As this 2013 disaster in Texas revealed, when around 50 tons of ammonium nitrate laid waste to a fertilizer plant and the surrounding community, leaving 15 dead, with more than 100 injured. This explosion happened at a facility storing a fraction of the ammonium nitrate present in the Winston-Salem plant. a fact that would come to haunt the local residents. January the 31st, 2022, at approximately 8 p.m., a passerby noticed smoke billowing from the plant. Chad Nance was at home asleep.
My partner wakes me up to tell me that there is a situation 6 miles from the house. She said it's a fertilizer plant and it's on fire.
First responders rushed to the scene and arrived to an inferno.
Within an hour, the disaster was escalating fast.
Paralegal Danielle Jessera was working late when she heard the news.
We were working on some cases, and I didn't know all the implications. I didn't even hear much about it. I just said, suit up, we're going down.
At the plant, firefighters discovered that ammonium nitrate wasn't the only dangerous chemical on site.
There's fertilizer in that building, also propane bottles are stored. It is adjacent to an ammonium nitrate area.
With gas also in storage, authorities feared a catastrophic reaction.
There were reports of explosions coming from the plant.
We've got flammable liquid running into all the ammonium nitrate. We've got active explosions going on too.
Danielle witnessed the scale of the fire firsthand and discovered the magnitude of the danger.
There was a big whiteboard, and in red, they had the worst case scenarios written down. Basically, the worst case scenario is that all of Winston and more blows up.
To protect the local population, around 6,000 people had to be evacuated, and fast.
The fire department started taking fire trucks and riding around making announcements saying, please get out of your home.
But the danger wasn't limited to residents. Firefighters soon realized this was a battle they couldn't win.
Command to all units. We're going to evacuate the scene. Leave any equipment on the ground. Just leave it.
We weren't prepared for this. We weren't prepared.
With the scene too dangerous for firefighters, the blaze burned through the night. When morning came, the damage was clear for all to see. Yet the fire was still burning.
The entire area of Winston-Salem was completely engulfed in a thick, acrid smoke. You couldn't see the sun. You couldn't see the sky.
As fears of a blast subsided, fire crews returned. But the wreckage continued to burn for days.
And the smoke sat on my neighborhood for 4 days. This was literally as if you were adjacent to a forest fire.
It was brutal. I mean, just walking outside in our area was brutal.
Finally, after 4 days, the fire was extinguished. But as residents waited for the smoke to clear, word began to spread that the whole city had come close to total annihilation. Authorities immediately launched an investigation, and one culprit appeared to be the building itself. Associate Professor of Chemistry John Merle explains.
An official report hasn't been made yet, but it seems that due to the age of the building, it could have been a result of an electrical issue or some other failure with the building.
The trigger may take years to establish, but there was another question. The facility was intended to store flammable chemicals. So why had the blaze been able to spread so quickly? Here, historic regulations appeared to come into play.
So the chemicals, from what I understand, were stored in a wooden building. Doing the research, I saw that they weren't required to have sprinklers because when the building was built, back in the 1930s, sprinklers were not required.
That explained the swift spread of the blaze, but there was another outstanding mystery. At the time, the plant was heavily stocked with ammonium nitrate and other volatile chemicals. So why had the fire simmered instead of exploding? Like this 2013 Texas incident.
Looking at the chemical inventory, they actually found 600 tons when the fire broke out.
To put this into perspective, 2 tons of ammonium nitrate mixed with other chemicals has the explosive power of 10 tons of TNT. This place had 600 tons of the stuff. If it went off, the devastation would be too vast to comprehend.
I don't think that anybody had any clue at all.
In Texas, just 50 tons of ammonium nitrate triggered the devastating explosion. So what had prevented a much worse disaster from happening here? Ironically, it seems the rapid spread of fire through the wooden building was a blessing in disguise.
A confined space is crucial to an explosion, containing increasing pressure and temperature like a bomb casing until it fails, releasing a massive blast.
Because the building burnt down, this avoided volatile molecules from getting trapped inside the building and building up pressure and temperature that prevented the explosion from occurring.
Winston-Salem had experienced a miraculous escape, but questions lingered. Why had the fire burned for so long? John Merle has a theory.
Here we have 3 piles of chemicals. So the first one's going to be the ammonium nitrate. You can see there are some areas where it's starting to melt, but there is no fire. It can take a lot of heat as long as there's not a buildup of pressure. The next one will be pure sawdust. Some of the sawdust is lighting on fire, but the fire is generally not sustained. The last pile is the mixture of sawdust and ammonium nitrate. So as you can see, this will burn until the fuel is completely consumed. If there is a lot of fuel, as in the case of the fertilizer plant, then it can burn for quite a long time.
The official cause of the fire has yet to be released, but experts and the people of Winston-Salem are forever changed.
We have to look at this as a lesson.
The best thing to do moving forward is to ensure that the storage facilities are as safe as possible. Ammonium nitrate should be pure. It should be stored on its own in a well-ventilated area and a building that is not susceptible to fire.
There is hope that a change in regulations will allow residents to rest easy.
The solution is taking legacy industrial plants like this that deal with hazardous materials and moving them outside of city limits away from where people live. It's that simple.
Big infrastructure can be key to bringing the world together. But when trouble strikes, those crucial connections can cause major headaches. Like this disaster in Canada, a crossing catastrophe on the nation's most vital highway.
There was no warning. A section of the bridge lifted almost 60 centimeters into the air.
A crucial link gone in the blink of an eye.
We were cut off from all of the necessary amenities that one would need to survive.
And a race against time to find a solution for the entire nation.
The reality is if that bridge were catastrophically lost, Canada would be cut in half for a long time.
Canada is the second largest country on Earth. This vast wilderness is connected east to west by one of the world's longest national roads. Spanning nearly 8,000 kilometers, the TransCanada Highway.
The TransCanada Highway is like Canada's spine, linking the nation's provinces from the Atlantic to the Pacific coasts. It's a vital connection for this huge country.
And a crucial connection for remote communities like this. The small town of Nipigon, which sits just north of the Great Lakes.
Hey guys.
Richard Harvey has been mayor here for more than 16 years.
I'm born and raised in Nipigon. There is something that's just really special about this area. The immensity of Lake Superior, the wildlife we have around here, the natural beauty. It's a community, not just a place to live.
While the town has a population of less than 2,000, it's home to one of the most important parts of the entire TransCanada highway. Completed in 2018, the Nipigon Bridge is an integral part of Canada's entire rail and road transportation network, carrying an estimated $100 million worth of goods every single day. Yet most people don't even know it's here.
Most people have no idea that there is such a place like this in Canada, and we're shocked that people don't realize how significant it is. It is identified as one of the critical infrastructures for the nation. If that bridge were catastrophically lost, Canada would be cut in half for a long time.
From the 1970s, the nation relied on this older two-lane span. But as traffic soared, it was clear that a bigger, stronger bridge was needed.
They recognized this as being a critical infrastructure and came to us with the proposal of doing a cable-stay bridge, the first cable-stay bridge ever built in Ontario. Just really an engineering masterpiece.
One major challenge was to achieve the necessary size and traffic capacity without impacting the Nipigon River below.
This area boasts some of the best trout fishing around, so you really want to avoid anything that can upset the environment. With a cable stay bridge, there's no need to sink piers deep into the riverbed.
But engineers didn't just have to contend with the river. Canada's harsh winters can make construction difficult too. As forensic engineer Jeff Archibald explains,
some of the challenges for doing a bridge in Northern Ontario include the incredible temperature variations. We'll typically go from 90 degrees Fahrenheit in the summer to minus 60 in the winter. So we're talking about 150 degrees of temperature difference.
Steel grows and shrinks with the weather fluctuations, so each of the main girders was designed to be held in place by expansion joints that literally allowed the bridge to move as needed.
If you didn't take into account that the bridge has to expand and contract with varying temperatures, you'd actually get buckling. Think about a straw where you push on the ends, it will buckle. And then, of course, it becomes undrivable and unsafe.
The new bridge would be built parallel to the old existing crossing. Once the first half was complete, traffic would switch from the old to the new spans. The old bridge would be demolished, and the remaining half of the new bridge would be built, accommodating 4 lanes of traffic in total. But the first crossing of its kind in this province was about to make global headlines for all the wrong reasons. Sunday, January the 10th, 2016, just outside Nipigon. The first half of the new bridge was complete. For Mayor Richard Harvey, it was just another cold Canadian winter's day.
Come home from church, and I was sitting down having a coffee, and a friend of mine called and said, "Hey, Richard, I hear your bridge broke." I thought he was joking.
But this was no joke. Just 42 days after opening, a section on the western end of the bridge had suddenly fractured, rising 60 centimeters into the air.
I got in my vehicle and drove down there, and lo and behold, the west side of the bridge, there was a drop. Not a good situation.
First responders and engineers rushed to the scene.
This one bridge disaster effectively split Canada in half.
Traffic was backing up for miles. And you got to understand, every good that is being transported across Canada is going across this bridge.
With northerly winds and freezing temperatures sweeping through the area, it wasn't just the traffic that was in trouble. Communities across the province declared a state of emergency. Marcus Hardy is chief of the Red Rock Indian Band.
We have a lot of elderly in the community, people with overall health issues. We were cut off from food, for medication, all of the necessary amenities that one would need to survive.
No one knew what had happened or just how long this bridge would be down. But what they did know was that they needed to find a solution fast.
While luckily no one was hurt, people wanted answers. How could a bridge that was vital for the entire country break after just 6 weeks? The Ministry of Transportation launched an immediate investigation as news of the catastrophe spread.
All of a sudden, you know, this is on the national news, all over the United States, Europe.
The problem was clear for all to see. The northwestern expansion joint had failed, and the tension from the main cables had pulled the deck vertically by 60 centimeters. The question was why? Forensic engineer Jeff Archibald knows the case.
For a bridge such as the Nipigon River Bridge, one of the key components is going to be the end bearings. These bearings have to allow for the fact that the bridge is going to get longer and shorter depending on the temperature, as well as 80,000-pound trucks driving over it, which are going to cause other rotations, deflections, and all sorts of loads.
As Jeff demonstrates, the system allowing the bridge to expand and contract as needed is complex and multifaceted.
We're looking at a model to show the primary components of the beam and bearing on the northwest end of the Nipigon River Bridge. We've got the I-beam here. The I-beam or girder was bolted down to what was called a shoe plate. So we have a shoe plate here. You've got expansion and contraction, which would cause the end of the beam and the bearing to slide in this direction.
But the expansion joint isn't just exposed to lateral movements. With this type of bridge, the suspension cables were pulling upwards on the ends of the decks. And the investigation discovered there was a problem with the bolts holding everything in place.
On one connection, all 40 bolts that kept the bridge level had completely fractured. What they didn't know was why.
The failed bolts were sent for testing at Canada's leading research facility, the National Research Council. And what they discovered was shocking.
To cope with the huge forces at play, the bolts should have been tightly secured in place during construction. But here that hadn't happened.
And what that meant is bolts, especially on the ends, saw more stress than they normally would see. And because they weren't pre-stressed, what happened is bolts at the end failed.
The combination of temperature fluctuations, heavy loads from traffic, and the upward pull from the cables strained the bolts. And one by one, they failed.
When one bolt fails, it stresses the other 39 until another one fails. And you get a domino effect until there's nothing left to hold that bridge down.
Eventually, bit by bit, bolt after bolt starts to fail until finally the west end of the bridge moves up 2 feet.
The solution was as simple as it was ingenious. They would push the raised section back down using hundreds of tons of concrete.
Crews used brute force and more than 100 concrete barriers to level part of the bridge.
Less than 24 hours after the disaster, the bridge was partially reopened, while work continued on a permanent solution, this time with securely fastened bolts. Chief Marcus Hardy was part of the team.
I was actually an iron worker on that bridge after the catastrophe, so I got to see exactly, what was involved in making the bridge, in putting it all together.
On February the 25th, 2016, just 42 days after the failure, the Nipigon Bridge was repaired, and Canada was back on the road again.
The big lesson learned for all of Canada is that this is an important infrastructure. that Nippigan is an important community.
Simply because of some loose bolts, Canada's transcontinental highway was sliced in two. It's a clear reminder that in engineering, even the smallest components play a major role.
When they build big, engineers must always consider the best materials for the job. Any vulnerability, and the outcome could be devastating. Like this disaster in New Zealand, that was weakening a building from the inside out,
A minor leak can turn into a major disaster.
causing fear for residents.
There was evidence that there is lots of trouble.
And threatening a devastating failure.
There could be a catastrophic event, a balcony dropping off, people getting injured and possibly killed.
If the support fails, there's a risk of total collapse.
New Zealand, in the South Pacific, is a land of extremes, from its volcanoes and glaciers to notoriously wild weather. It's also home to the most southerly capital city in the world.
Wellington is often ranked as one of the most livable cities on the planet, and the vast majority of residents live on or around its scenic coastline.
This coastal capital might be popular, but it's the windiest city on Earth. Phil Pennington is a local journalist.
We frequently have winds of a 120, 140 k that in London would be a hurricane. Here that is a regular occurrence.
Wild weather isn't the only thing rocking Wellington. The city sits on an earthquake hotspot.
Because of the fault lines that come through Wellington, living in a real shaky place.
New Zealanders discovered long ago that in a quake, brick and stone buildings didn't fare as well as their timber neighbours. And today, like in many countries, nearly every home in New Zealand is built from wood.
Timber is one of the oldest construction materials, but it's also one of the world's top performers. When treated, it can be stronger than steel.
But it's more than just strength. In a shaky, windy country, timber's ability to flex with movement makes it the perfect choice. Richard Foreman is an architect.
In New Zealand, we have high wind pressure and buildings actually move over time. So timber has been used very successfully, and also it's pretty good in earthquakes.
Here, this success means wood isn't just used for houses. It's even the strength behind some much larger structures. Like this 11-storey apartment complex built in 1997. Roger Levy is CEO of New Zealand's Homeowners and Buyers Association.
It's an award-winning building. It's effectively 2 blocks. Most of the apartments span the 2 blocks with walkways between.
Like many other buildings, the stylish exterior covers a skeleton made from a timber frame. But here, the wood also helps anchor a standout design feature: cantilevered balconies.
Projecting or cantilevered balconies are relatively simple constructions. You have beams anchored inside the building that jut out, allowing you to rest your balcony on top.
For more than a decade, residents enjoyed their prime views across Wellington. But this award-winning building in the world's windiest city was about to be hit by a storm that ravaged the country. April 2014, and across New Zealand, wooden buildings constructed in the mid-90s were coming under scrutiny. The cause of concern wasn't earthquakes, but the nation's challenging weather.
We started to see issues arising with properties where inside the units moisture was showing up.
Any moisture inside a wooden framed building is bad news.
Timber is strong, durable, and can last for centuries. But if water gets inside, it can rot. And if left untreated, this can severely reduce its strength.
In Wellington, inspections of the 11-story apartment building revealed that it too was suffering from rotting wood. Sidhu Matwani owns an apartment here.
So a structural engineer came and looked. There was enough evidence from their expert eye that there is lots of trouble.
The rot was discovered near the surface of the structure, where the beams that support the cantilevered balconies emerged into the open air, leaving residents deeply concerned.
Cantilever balconies have no built-in redundancy. If the support fails, there's a risk of total collapse.
There's a lot of concern. At some point, there could be a catastrophic event of some description, a balcony dropping off, breaking, people getting injured and possibly killed.
The only solution: to close off every balcony in the building. And owners were demanding to know why their dream views of the capital had turned into a nightmare. Further investigations revealed the issue went deeper, exposing a potential flaw in the exterior cladding. For owners like Sidhu Matwani, the news was bad.
They did invasive inspections and then basically found that it was not just a localized issue. There is a problem with the cladding, that wherever they opened, there was signs of water inside.
In the world's windiest city, rain will find and invade any flaw in the exterior.
With the combination of wind and rain, you get wind-driven rain, which is far more, penetrates far more than if it just rains straight down.
Water getting inside the building was only the start of the problem, as it soaked and rotted the wooden frame. Architect Richard Foreman explains.
One of the things that happens is that rain gets drawn behind the cladding and sits under the timber, and of course it rots away, which was the case in this building.
And investigations revealed another potential route for the water to get deep inside, along the beams supporting the cantilever balconies.
If we have balconies that have the structure running from the inside to the outside, how you protect that from moisture getting in and damaging the framing at that point where it comes from the inside to the outside is tricky.
If not properly sealed against water, the cantilever beams can act like a wick, drawing water to their anchor points deep inside the building.
With the cantilevers, where if that's not properly constructed, you get moisture getting sucked back into the structural beams that go back into the building, then the whole structures were starting to become unsound and of concern.
Whether the cladding, the beams, or both were allowing the water in, the real extent of the problem was worrying for everyone.
We don't know how much timber has been damaged behind the cladding until you open up.
It seems the only real solution would be to remove the outer covering, repair any damage to the frame, then reclad the entire structure, at an estimated cost of $22 million.
The repair costs were estimated to be 3 times the original construction costs. The good news is that the damage was spotted before there was a major disaster.
That's a small consolation for owners, forbidden from enjoying the view from their balconies until a fix is found.
As far as I know, the project to do the big fix, definitely not affordable.
Meanwhile, many hope the countrywide problems with timber-framed buildings will force the industry to find a permanent solution for the future. In big construction, every detail, no matter how small, has to be worked out with extreme precision. Even a minor miscalculation can lead to a major disaster. Like this catastrophe in Northern Europe. A vital border crossing that was way off the mark.
This should have brought 2 nations together. Instead, it literally kept them apart.
An engineering tale of two cities that didn't go according to plan.
Da hat man festgestellt, ups, hier stimmt was nicht. Unglaublich.
And a seemingly straightforward calculation that went wrong not once, but twice over.
This boiled down to simple mathematics, but it added up to a double engineering disaster.
The Rhine is one of Europe's most important rivers, flowing through 6 countries and defining national borders, including this historic location between Switzerland and Germany. On one side lies the German town of Laufenburg, and on the other lies the Swiss town of Laufenburg.
This isn't some strange coincidence. These two towns were originally one and the same until 1801, when Napoleon split them in two after victory in battle.
Not only do these two towns share a name and a border, they also share a common bond, remaining connected throughout the centuries by this old toll bridge. Marcus van Nijenhof is a boat captain and local tour guide.
So, wir befinden uns jetzt oberhalb der alten Zollbrücke. Sie wurde im Jahre 1908 erneuert. Der historische Stadtkern von Laufenburg ist einzigartig und er hat eine besondere Geschichte. Eine Stadt auf 2 Länder.
By 2003, it was clear that the old customs bridge could no longer cope with the demands of modern-day traffic.
Ist hier der ganze Straßenverkehr über diese Brücke gelaufen. Die Brücke hatte 2 Fahrspuren, aber der Verkehr in der Altstadt, da hat sich da immer gestaut, da war so ein richtiges Nadelöhr.
In the spirit of cooperation, both Laufenburgs agreed it was time for an upgrade.
Aber mittlerweile ist diese alte Zollbrücke eine reine Fußgängerbrücke. Also die ist eigentlich für den öffentlichen Straßenverkehr nicht mehr freigegeben.
The result was this. Just downriver from the historic town, the 225-meter-long Hoch-Rheinbrücke, or High Rhine Bridge. The pre-stressed concrete bridge was completed in 2004 at a cost of around 10 million euros.
2 countries came together to build a modern crossing, and construction costs will be shared equally.
In a further demonstration of unity, the bridge would be built simultaneously from both ends.
When you have 2 nations building from opposite sides of a bridge, one thing that's crucial is that you meet in the middle. But it's not always as simple as it sounds.
In a city divided by a river, a border, and even Napoleon Bonaparte, this bridge was about to make history for all the wrong reasons. Winter 2003. Construction of the new High Rhine Bridge was well underway, and it was undergoing a routine inspection ahead of the planned holiday season shutdown. Fabrice Müller is a local journalist.
Es war kurz vor Heiligabend, als die Ingenieure mit Schrecken feststellen mussten, dass man bei der Brücke einen Berechnungsfehler gemacht hat.
The bridge wouldn't be unifying anything as it currently stood. The inspection discovered that the Swiss side was lower than the German side, by a considerable margin.
This wasn't a tiny mistake. The 2 ends were out by over half a meter.
Instead of happy holidays, this had become a nightmare before Christmas.
Diese Brücke hat es geschafft, in die Geschichtsbücher einzugehen. Und wie man das letzte Drittel eingeschaltet hatte, da hat man festgestellt, ups, hier stimmt was nicht. Ja, ist eigentlich unglaublich.
This was an early Christmas present neither country wanted.
So how had a bridge, built by 2 countries with a reputation for precision engineering, gone so drastically off course? The mistake, it seems, could be traced all the way back to the drawing board. Dietmar Adam is a professor of geotechnical engineering.
So the general process of planning a bridge is to find, first of all, the alignment. And when you know this, you do some ground investigation, soil sampling to get to know about the ground conditions. And then finally, you can do all the design of the bridge in detail.
But it was in the last part of the plan that things began to unravel.
In the designing stage, it was taken into account that there are different reference altitudes due to different sea levels.
Sea level is the base level for measuring elevation or depth. However, winds, currents, temperature, even gravity create variations, so the level can be different depending on where you take your readings.
There are differences between the different locations.
Here, this variation led to a miscalculation in one crucial detail: which sea each country was referring to.
They might be neighbours, but Germany uses the North Sea for its base level, whereas Switzerland uses the Mediterranean. Crucially, there's a difference.
Engineers were well aware that the Mediterranean level is 27 centimetres lower than the North Sea base level.
So the difference of the reference altitude was well known in advance. And it was the plan to correct it on the Swiss side.
This plan was seemingly straightforward. What could possibly go wrong?
Engineers factored the difference into their calculations. The only problem was they went the wrong way, effectively doubling the difference instead of cancelling it out.
Instead of raising the level on the Swiss side by the required 27 centimetres, engineers went the other way, lowering it by a further 27, meaning the bridge was now out by 54 centimetres.
I would say 99.9% of all cases, this will not happen because it is well known to the engineers that there are different reference altitudes between two countries.
So one side had to say to the other, sorry, we got the numbers the wrong way round. This had all the makings of a long-running catastrophe.
There was a double mistake. It happens, but it does not happen very often. It is really very seldom.
With the two countries starkly out of alignment, a solution was needed.
Like any situation where there's a difference between two nations, most of the time, the perfect answer is to meet in the middle.
Here they achieved that by raising the abutment on the German side by the now required 54 centimetres.
Fortunately, it was early enough that they realized the mistake. So the bridge foundation on the Swiss side was already finished, and on the German side they were a bit behind.
So konnte man den Fehler noch korrigieren, indem man halt auf der deutschen Seite den Brückenpfeiler erhöhen musste. Hier ist die Schweizer Seite, das ist die deutsche Seite. Und auf der deutschen Seite der Brückenpfeiler, der ist sichtbar höher wie der auf der Schweizer Seite.
Das war natürlich peinlich und man musste das korrigieren. Heute merkt man eigentlich davon als Autofahrer nichts mehr viel davon.
With the mistake corrected, the bridge was completed and finally opened on December the 17th, 2004. Almost a year after the disastrous Christmas discovery.
Mistakes can happen, but there is always a solution done by engineers.
The lesson here is simple. Always double check your calculations. And always make sure you know the difference between up and down.